I think I'll start by just, let me say again where we left off. So we write down this Laplace comparison theorem we left off on. And let me say a few more words about what we were doing at the end, because it got a little rushed. I mean, I won't do it line by line, but let me at least make sure all the main points are sort of clear, and it gets reduced down to a point where it's an ODE discussion, and you can sort of count that as homework. And I'll be specific about when we get to this point. Let's first just state what the Laplace comparison theorem was, because this is what we want to prove right now. So we are considering some Riemannian manifold, M and G, which was supposed to be complete. With Ricci curvature bounded from below by n minus 1k. I think when I wrote it yesterday, I put a minus sign there. That's habit for me. There's no minus sign the way this is being written. Then what? Then the Laplacian of the distance function at some point taken as a distribution. Is a measure. Mu, which, if we decompose it into its absolutely continuous and singular parts with respect to the Riemannian volume measure, we have two statements that are pretty nice. On the one hand, I'll do it here. On the absolutely continuous part, so that this is on the smooth part of the distance function. So this thing is literally just the computation of the Laplacian of the distance function at this point. It's bounded from above by what the corresponding Laplacian of a distance function is on the space forms. So this was n minus 1 times s and k prime over s and k evaluated at the distance function. And our second statement was that the singular part is actually non-positive. It has a sign. This is the most important thing, because, well, I mean, when you want to actually exploit what the Laplacian of a function is, right? I mean, even in a distributional sense, sometimes, I mean, there's going to be a piece where we can kind of bound the control of it, and this we have no idea what this thing is doing. But the fact that it has a sign means that down the road, we're going to be able to throw away it. I mean, just throw it away in our estimates. So this is going to be absolutely crucial. So it has a sign, and it's supported on the critical set of X. So yesterday, very quickly, we went through what the proof of 1 was. But let me just say sort of what the main points were again, because this was done much too fast, because we were at the end. So quotes, the proof of 1 looked like the following. So the idea was that we picked a point x, and then we picked some other point y inside our space. And so, right, let's say proof of 1 for k equals 0. So for Ricci non-negative. So what we want is that if y is in M minus the critical set, so it's a smooth point, we simply want to show that the Laplacian of the distance function here is less than or equal to n minus 1 over the value of the distance function at this point. So what we did was we said, OK, well, what do we know about this set? The nice thing we knew about this set was that one of the properties we had is that the distance function on this set was smooth. Well, the distance function on this set minus x is smooth. It's obviously not smooth at the origin, but everywhere else it's smooth. And we had that if we had some point inside this set, then the geodesic from x to y is also in that set. So not only is the distance function smooth here, it's smooth everywhere along this geodesic, which made it very legitimate to do computations along this geodesic. So that once we actually picked a minimizing GDS at gamma of t, what we did is we just rewrote this by saying m of t was just the value of the Laplacian of the distance function, just evaluated at gamma of t. That way it became a real valued function on R. Much better. And so rewritten this way, what we wanted to show was that m of t is less than or equal to n minus 1 over t. Right? Because the distance, if this is a unit speed geodesic from gamma of t to x, is just t. And we can just define this thing as being m naught of t, say, just because. And what we did, and that this was a very simple computation, but the main thing to do is you got to learn to work in coordinates and commute things and just sort of get comfortable with this, is that we showed that under the non-negative Ricci assumption, that d dt of m plus m squared over n minus 1 was less than or equal to 0. So remember, there are two key steps here, right? First is that there's a term when you do this computation that involved the Ricci, but the Ricci was applied to the gradient of the distance function twice, which meant it had a sign, and we got to drop it here. And the second point that was important yesterday was the fact that, so this is the Laplacian of the distance function, which if you want to rethink of this, it's the trace of the Hessian. And so what we really had over here was actually a Hessian of d squared, but we used sort of a standard estimate that works for any matrices to replace that by just the Laplacian of d, but we gain the n minus 1 factor on the denominator. And now the key point, though, is that to identify 0 now as actually being the thing that m naught actually solves, which, if you want to write this in a form that will be more conducive to maximum principles, what you want to do is say this d dt of m naught minus m. So we want this thing to be non-negative forever, right? That's the goal. It is less than or equal to, so we just, let me try to do that one over there. This comes over here. So this becomes minus m naught minus m times m plus m naught over n minus 1. So I just collect these two terms together. So why is this helpful for a maximum principle? Because it's saying that, I mean, imagine you just start with this thing being non-negative. Imagine you knew this. This is a tricky point because it's blowing up, but let's ignore this for a second. Nice, smooth, whatever. If this thing started to be non-negative, then it says as long as this thing is non-negative, then the rate of change is less than or equal to 0. So oops, I got a sign wrong here. Bigger and equal. Thank you, because I put it on this side. So as long as this thing is non-negative, then the rate of change is non-negative, well, which means that this thing actually just goes up. It can never sort of go through the 0 points. And the last point you would need, and to actually make this all rigorous, is that the only tricky point in all of this is that m and m naught blow up at the origin. So you're saying, how do I do a maximum principle? Well, to do a maximum principle, what you have to do is you have to write out that by using exponential coordinates, and this is a great exercise. By using exponential coordinates, you see that m of t, that is just to say the Laplacian of the distance function in a small neighborhood of x, is always, for any smooth manifold, it doesn't matter, no Ricci bounds, no nothing, just write in small coordinates. This thing is always equal to n minus 1 over t plus some O of 1. So some function, but the function is bounded uniformly in that neighborhood. This plus this implies this. That's homework. I'll give you hints later if you want to think about it for a while and we can talk about it. Because it's a good exercise and it's just ODE theory. So let's. Okay, but that was sort of just a brief review to try to be a little bit more precise of where we left off yesterday. Much more important here. Well, not much more important, but this by itself is not helpful. It's interesting. I mean, knowing that the Laplacian of the distance function has an upper bound on the smooth part is kind of cool. But it is by itself not helpful. So when you do analysis, if you want to use that you have estimates on the Laplacian of a function, then you need estimates on the Laplacian of the function. The Laplacian of the function on some open-end subset is not sufficient. right? Not if the thing isn't smooth, so this says something about the whole thing. So to actually apply this in practice and make use of it, we need to know something about the Laplacian of the distance function everywhere, in particular on the non-smooth part. So we need to know something about the Laplacian away from the smooth part. That is, we need to prove two. We need to prove that as a distribution, this thing is supported on the critical set, and it is a measure with a sign. So most of this proof, by the way, really has nothing to do with geometry. It's a nice analysis statement. It's sort of just a general sort of approach of how you try to prove such things and understand such things. So proof of two. It's also very hard to find a good reference that actually does this carefully, so I thought it was worth doing. Okay, so again, we're only going to prove two under the non-negative. Well, I don't think non-negative, I mean, the sign of the Ricci doesn't really matter, so whatever. Okay, first statement. So crash course. What the heck is the Laplacian of the distance function if this isn't a smooth thing? So remember, you can take the Laplacian of anything you want. I mean, smooth, not smooth, whatever. You just don't get a function, you get a distribution. So by definition, what that means is that if you give it a smooth function, say a smooth function with compact support just to make life happy, then it gives you a number out of it. And how do you get that number? So by definition, this thing here is a distribution, which means that, let's let phi be smooth. And for the sake of argument, compactly supported. Then this will act on a function phi to give you a number. And it does it by integrating over the manifold the Laplacian of phi times the distance function. Right? So the point is that if the distance function were itself a smooth function, then this is exactly what the Laplacian of the distance function would do to act on some smooth function. Right? You just multiply it by the function integrate, and that's what its action would be. You do two integration by parts, and you move the Laplacian from the distance function to the Laplacian of phi. No problem. But the point is that this makes complete sense as a distribution, no matter what the distance function is, as long as it's, it itself can act on a smooth function. It just itself has to be a distribution. So it takes very few requirements. Fine. So by definition, we have this. The way it's written, it looks like, the point here, right, is that as a distribution, it looks like it depends on two derivatives of phi. So if we want this, then we want to vary phi around in a way that this number changes in a continuous way. It looks like phi we have to have it varying in a C2 way, right? And the point of it being a measure is that that's not true, that this is just an artifice of the way we're writing it. That in fact, phi only has to move in a C0 way in order for this number to change continuously. So we have to find a better way of rewriting this. But this is the definition, right? Definition. Okay, so what do you do? Well, you do the following. So remember, if we have our point x here, we've got our critical set. And last time we had a way of sort of pushing away from the critical set. So we had our CXR, right? So it was the set. So the critical set was exactly the set of points where we looked at x, we moved along g at sx, and we stopped whenever it wasn't minimizing anymore, right? And CXR meant that you stopped either there or within distance r of that g at sx. So if this was some g at sx, we could have stopped here to get to the critical point, or we could have stopped at distance r back to get to CXR. CXR is this thing here. So it's just it's going to be some open set whose measure is going to 0 as r goes to 0, and it's converging in a very reasonable sense to Cx. That's what it's doing. So in particular, this is some nice function. This is a Lipschitz function even. It's a pretty well-behaved function. This is some compactly supported smooth function itself. So we can simply write this as the limit, as r goes to 0, of the integral of m minus CXR of the Laplacian of phi dx. So all I'm saying is that we're throwing off a set whose measure is going to 0, taking that limit, and certainly the limit of these integrals is going to be this integral, because this is some bounded something over some set whose volume is going to 0. But now this is much better already. Why? Because the distance function is legitimately smooth on this. So we can start to do manipulations with this expression without being too scared of what's going to happen. So in particular, we can do an integration by parts. Right? Use a Stokes theorem. So what's our Stokes theorem says? It says that if we integrate by parts once, then we get two terms. Well, one is that so this is the divergence of the gradient, remember? So when we actually move over the divergence, we get a gradient with a minus sign. So this is just equal to exactly minus the integral of m minus CXR of the gradient of phi, the gradient of the distance function. But that's not all we get, right? I mean, if this is a Stokes theorem and this is some nice smooth something with boundary, we have to have a boundary term from this, right? This is where the distribution comes from, right? If this were some nice smooth function, we would kind of expect there to be no boundary term when we do this, right? But we're not going to be so sure of that this time. The boundary term just being the integral over the boundary of basically the same thing, but let's say m minus CXR of, well, that means we drop the divergence, we look at the gradient in the normal direction of phi, and multiply by the distance function d sub x. It's not, but it is, I mean, I'm sliding this a little bit under the rug, but it is well behaved. That's actually very easy to check from the definition. You don't need fancy stuff for it, because it's really the image of something from upstairs in the tangent space. I mean, it's a star-shaped region. You can get enough boundary regularity for this normal to make sense almost everywhere in a perfectly reasonable sense. Pretend smooth, though. There's absolutely no harm in it. I mean, just if this bothers you. OK. But now let's rewrite this again. We're going to be doing a lot of rewriting. Let's just keep this term the way it is for the moment and not worry about it. Let's first deal with this boundary term. So in fact, what I want to do with this boundary term is more or less just reverse, right? So that this region, that this CXR here, right? Here's my CXRs before. Then if I'm integrating over the boundary here, I could just as easily, with the minus sign, do an integration by parts, but make it into an integral over CXR instead of m minus CXR. It doesn't really matter. I just reverse it out. So this becomes minus the integral of, and it's the same divergence theorem, so it means the Laplacian of phi times dx over CXR. So I just did another Stokes theorem, but I viewed this thing as not being the boundary of m minus CXR, but I view it as being the boundary of CXR. But remember, the normal switches direction, so I got to get a minus sign. So this isn't the normal to that. It's minus the normal. OK, but this is very good, right? Because what is this thing? This is some bounded something. This is some bounded something. This is some compact subset. And this is something whose volume is going to 0. So that this integral as r goes to 0, well, it just goes to 0, right? The volume of this set is going to 0, and these are both bounded. So this term just goes away. So there's nothing to worry about from this guy. So that is to say, it's just, we're back at the point where we have the limit of minus the gradient of phi, gradient of dx, over m minus CXR. So if you want, by the way, already this is interesting, right, without doing anything else. Because if we wanted to, which we're not gonna, but I'm going to write it just to sort of explain morals of what's going on, we could now take this limit, right, because this is a Lipschitz function, and this is some smooth function. So this would, in fact, limit to the integral over m of minus gradient of phi gradient of dx. And now what we have is that this distribution, which originally depended on two derivatives of phi, now just depends on one. So we've already at least seen something, right? We've seen that the fact that it depended on two derivatives of phi was fake. We've already seen that just by doing this first step. And in fact, only now seems to depend on one derivative. We want to get rid of that derivative too. But I mean, just at this stage alone, we've kind of already recovered that. It's a distribution of just one derivative, not two. But we're not going to actually take this limit. Instead, we're going to play the exact same game again. I mean, what would you do if the distance function was a smooth function? You just do another integration by parts. Right? You do another integration by parts, you get another boundary term. And if dx were a smooth function, you want to play a game like this and try to say that it goes away again. Right? Well, we're going to get stuck this time. It's not going to go away. But you'd want, I mean, this is how you would try to approach. And so this is what we're going to do here and just see what happens. So we integrate by parts one more time and throw it over there. Because again, it's nice and smooth on this region. There's no question about this. So this becomes, well, this first term here becomes, well, we throw in another minus sign. And we get phi times the Laplacian of the distance function. That's nice. And now our boundary term again is going to become minus the integral over boundary of m minus cxr of, now it's phi, but since we're throwing this one off, it's the normal and the dx direction. Okay. Now, the point is that if dx were smooth everywhere, we would play the exact same game here, right? We would turn this into an integral over cxr and make it go to 0. But we just can't do that this time because it isn't smooth everywhere. I mean, that's not a legitimate computation anymore. So instead, we just want to study this thing itself individually. So what's the key point? So first off, it is not true that this goes to 0, right? So that's the first thing to sort of just kind of come to grips with. There's no reason for it to, and in fact, it does not. So this is a legitimate term. Now, let's try to at least say something, since we're doing that, let's go ahead and just write it out as something, right? So let's say this, now the, well, let's take these two limits individually for a second. So this limit here, well, there's no real problem for this limit here, because this is smooth on m minus cxr, and as r goes to 0, all that happens with this first term here is that we get the integral of phi times the Laplacian of the distance function. I mean, we can't integrate over m, but we integrate over the smooth part. Right? So it's exactly what we would want. This here, by the way, is exactly the absolutely continuous part, right, of this distribution, of this measure. If there were no boundary term, you would just stop here, and you would say, OK, well, the Laplacian is now a measure which is absolutely continuous, because that's the definition of what this thing is. For this term here, however, let's just write it out separately for a second. So this is boundary of m minus cxr of phi times dn dx. OK. Now, we would be a little stuck if we couldn't say more at this point. So there was a really important point that was mentioned about these CXRs yesterday. So that is something about their normals that were nicely behaved. So that if we were to take a point here and look at its normal. So here's the normal to our CXR, our boundary of our CXR, right? And if we were to look at the gradient of the distance function, right? So that means taking this geodesic here and looking at gamma dot. Then what we said was that the gradient of the distance function from this point in the direction of the normal, so that's exactly this, well, we said it had a sign. It was positive. So we're integrating phi here, on this hypersurface times something which is at least having a sign, non-negative. So what does that mean? That means for each r fixed, so this first term here we can just call the absolutely continuous part. So this is by definition. This thing applied to phi is this. So this is a measure. It acts on phi by just integrating phi times this function. Sign measure, of course, but measure. And this term here is, well, let's not take a limit. This is still too tricky. But these are themselves, for each r fixed, ignoring the limit, they are also measures. By definition, it acts on phi by integrating on this hypersurface your function times this. And it's not just any old measure. This is not signed. So phi sub r as a measure is non-negative. Okay. So what do we need to be done? We're almost done, right? I mean, we've said there's some absolutely continuous measure that's being applied to. And we have that it's a limit of some other measures. They are not absolutely continuous, right? You're integrating on some hypersurface, but whatever. They are measures being applied to phi. But how do you know the limit of these non-negative measures is itself a measure? So there's a nice general test for this. I'm debating on, I want to do this line by line, but I don't want to take the entire time to do it either. So let's certainly start with what we need. So mu sub r is a measure, right? That means we give it a set, it gives us a value. So what we need is that for every r positive, so big radius, that the measure of the ball of radius r is bounded. This mass can depend on the size of the ball we're looking at, but not on little r is the point. So that you get a sequence of measures with bounded mass. And there are standard measure theory arguments that say you're done. That you can pass to a subsequence anyway, and these things will converge. So if we had this, then immediately what we would know is that mu sub r, as measures, converge weakly to some measure mu. And you'd be done. That would be the statement. Because then over here, we would have that the Laplacian of the distance function applied to phi as a distribution is officially equal to the absolutely continuous part applied to phi plus whatever this thing is, or minus whatever this thing is, minus mu naught applied to phi. It's a measure, and that's all we've claimed, and so we're done. Yes?
But as you said, it's only up to subsequence.
Absolutely, right? But that's all you really need, right? Because, I mean, I could pick any r going to 0 I want, pick the subsequence, and this is still a true statement, right?
But it might depend on which one you take.
No, it doesn't depend on the function. That's the point. It converges as a measure. So there's a subsequence so that for every continuous function, no matter which one I pick, that will actually converge to the right value. So the value of this thing apply to that. Right? So the sequence depends on just the mu sub r, not on the function. So it's an honest measure convergence, not a... Okay. So instead of doing this, which I would actually really like to do, I'm going to tell you how to do it. And it's a quick exercise. Well, quick meaning it'll take you about 45 minutes, but it's a good exercise. there's nothing but computation involved. So let me just say what the key idea is. The point is that to even show this requires very deeply the fact that we already know it has a sign. Because it means that all we really have to do is let phi sub r be a smooth cutoff function. Such that phi sub r is identically 1 on the ball of radius big R around x, 0 outside the ball of radius 2r around x, then the measure of this thing on the ball of radius r is less than or equal to, well, this thing here as a function, right, it's a characteristic function, is less than or equal to this function. So since these are measures, that means it's less than or equal to this. And now the point is simply go back to this original computation here. Use the formula we've already proved, replace phi by phi sub r, and you can actually get your bound directly with the computation. I mean, that's cheating. It deserves 2 or 3 blackboards, but it is straightforward. The point is that this here is just something, and the Laplacian of the distance function applied to it. Well, the Laplacian of this thing is also some bounded something. So everything is bounded here, except arguably this. But since it has a sign, well, you've just bounded that. That's quick. You didn't have to follow that. But I'll take that for granted so we can move on. And then that's it, right? You get your measure and the theorem's proved. So it's a tricky theorem, but somehow there's nothing in here that isn't somehow classic techniques. So it's a good one to go through. I mean, this really is not geometry dependent what's happening here. This is a very standard thing. If I handed you a Lipschitz function, which was smooth on an open dense subset, and I told you to figure out what its Laplacian was as a distribution, same ideas will let you understand this. Right? So these are sort of key points. Okay. Last second questions, because I'm changing topics entirely. Fantastic. Okay, so those of you who have lost or otherwise gotten otherwise engaged, I am changing topics now. You can re-engage. So what is all this? This is, well, no. Let's do applications of this instead. I mean, it would be nice to, I mean, let's use this for something so we can see why anybody cares. I think maybe that's a nice thing to do. So let's apply this to something. So the first really nice theorem that separates spaces with lower Ricci curvature from normal spaces in the world goes back to really Gromov, way back when. So actually, really, I sort of started with Bishop, and Bishop just didn't quite push it as far as it could be pushed, and Gromov noticed it could be pushed further. So let's use this now to prove something. So this is called the volume comparison theorem. It's actually a great theorem. So let's consider the following theorem. So this is volume comparison. The proof of which is just going to basically be a 4-line application of this. So let's take some Riemannian manifold, and I'm always assuming complete when I say stuff, with a lower curvature Ricci bound. n minus 1k. So let's do something interesting. So for some point in M, let's look at the ball of radius r around this point. So here's our x. Here's our ball of radius r around x. And let's let Vr of x be the ratio of two things. Let's look at the volume of this ball. And let's compare it to something. Let's compare it to the volume of the ball of radius r and the corresponding space form. So by definition, this thing here is we look at our space forms that we defined yesterday. We look at a ball of constant curvature k. We look at any ball of radius r. It actually doesn't matter which one you look. It's all the same. And we look at its volume. And when we look at the ratio of these two things. Then ddr of this, so as a function of r, it's non-increasing. There will be a tremendous number of extensions of this theorem that play a very deep role in what's to come. But even by itself, it's an extremely useful thing. So let's prove it. So to prove it, let's note the following. I'll prove it for, as usual, Ricci non-negative, just because I don't want complicated functions floating around. So note that all we're saying then in this case is that Vr of x is the volume of the ball of radius r around x divided by some universal constant times r to the n. Right? So we're saying this is a monotone function. So note, so we just proved the Laplacian of the distance function was a measure with two pieces. And now this is somehow the key point about what I was saying. We don't ever want to deal with this piece here. But what we can say is that as a measure, since this is non-negative, it's less than or equal to just its absolutely continuous part, which is itself just less than or equal to n minus 1 over the distance function. So as a measure, this thing is just less than or equal to this measure here. Very simple measure. Which is, by the way, right, exactly what the Laplacian of the distance function on Euclidean space would look like. And a really nice way to write that, just because it looks cool, and it'll be more convenient so we don't have this nice little singular term here, is that if we look at the Laplacian of the distance function squared, then that's less than or equal to 2n. So this is with non-negative Ricci, right? I mean, that's where that's coming from. Right? Because you get 2 times the Laplacian of the distance function times the distance function. That kills this. But then you also get plus the gradient of the distance function squared, which is 1. So that just gives you the plus 1. Cover this up. OK, so then how do we prove the theorem? So proof of volume comparison. So Let's compute. So what is the rate of change of this thing? Well, what we're computing the rate of change here, right, is, so this is omega n minus 1 r to the minus n times the integral of 1 over the ball of radius r around x. So when we compute the rate of change of this, we have two terms, of course, right? We have to hit this term and we have to hit this term. If we hit the first term, we just get minus n. But then if we, well, let's just write it out. Rn minus 1, r to the minus n minus 1 times just the usual volume of the ball of radius r. And if we hit this term, then what is the rate of change of the volume of the ball of radius r, right? So this is sort of a standard formula. You should know if you don't. All it is just the volume of the sphere, right? So I mean, as the ball of radius r is changing, that rate of change is just equal to the volume of the boundary of that thing. And so this is plus omega n minus 1 r to the minus n times the volume. Well, let's just write it as the integral over the sphere of radius r of dvg. Now, basically, two semi-clever manipulations, and we're done. So first off, what's the first term, right? So the first term here is just exactly minus n r to the minus 1 of v sub r. Nothing else. The second term here is plus, let's rewrite this as, so what else is 1? I mean, let's just rewrite 1 as being the gradient of the distance function squared. Why not? That's 1. We can replace that. This is minus n r to the minus 1 times the volume of the ball of radius r. And let's even rewrite this a little bit, just because it's more interesting. So the gradient of the distance function, on the one hand, it's actually the normal direction, right? So this is we can take one of those gradients and make it just look like the normal direction to the sphere, right? The normal is exactly the gradient of the distance function. And we can get really crazy and say the other one, well, what is the value of the distance function on the sphere of radius r? It's just r, right? I mean, we're on the sphere of radius r. The value, I mean, this is a silly function on the sphere of radius r. Its value is just 1, or r, sorry. So what we can do is we can actually replace this with, say, the distance squared. But what happens when we do this, right? So we get a 2 down, and then we get a distance function times the gradient of the distance function, which means we have to divide by 1 over 2r. This is over omega n r to the n. And this is on the sphere of radius r. What is that? So this thing is, as a measure, the first term is just going to stay the way it is. And the second term here is going to become plus, let's just say 1 over 2r to omega n r to the n plus 1. But we can rewrite this second term here as being the integral over the ball of radius r of the Laplacian of the distance squared. Little care here that you want to think about, right? I mean, that this is a very, very important point just to think about a little bit. When I go from there to there, I mean as a measure, right? because you can't legitimately do a divergence theorem here. So there is a measure here when I'm writing this. Right? It is an expression that was basically, I tried to save it, right? It's this right here that I'm basically saving. But at this point, now we can do a sign, right? So this term here hasn't changed in a long time. It's just v sub r. This is just 2n, right? So this is less than or equal to 2n over 2 omega n r to the n plus 1. And then what's left over is the volume, because this became 2n, so I just integrate over the ball of radius r. It becomes the volume of the ball of radius r. But heck, so it's minus n, r to the minus 1 vr, plus, well, 2's go away. There's an n out here. And if I pull this r out, then what's left over is vr. I mean, 0. That's it. That right there. Okay, that's volume comparison theorem. So the rate of change of the ratio of these volumes is less than or equal to 0. Let's get rid of this. So let's do 2 applications of this. And these are tremendously important. I mean, these are the first things that this is. I mean, so the corollary here. So again, the fact that this ratio is monotone is interesting, but I mean, if you're not familiar with the subject, that there's still going to be a so what sort of setup here. So if the Ricci is bounded from below by something, minus 1k, then we have 2 things that hold. This is called doubling. What it means is that we want to understand somehow that the volumes of balls are well behaved on our space. And the first claim here is that if you have a lower Ricci bound, this is true. So let's say for all r less than or equal to 1 anyway, we're going to have that the volume of the ball of radius 2r around x is going to be less than or equal to some constant, depending on just the dimension, times the volume of the ball of radius r around x. So when we double the size of the ball, the volume does not go up that much. It doesn't change that much. It's basically saying that the volume of the ball of radius r is like a Holder function in r. It's not changing that quickly. Without the lower Ricci bound, this would be horribly wrong. And this is, I mean, when you're trying to sort of take analysis that you do on Euclidean space and say, hey, this analysis works on Riemannian manifolds. I mean, you know, if you're familiar with things like, you know, maximal functions, you know, I mean, just full of Rudin's book or any of this stuff, that this is implicit in everything that gets done there, even if it's never explicitly said, because on Euclidean space it's considered stupid and obvious. But the point is you get to a stuck point on a manifold, and you're going to find that 80% of the time it's this line right here that stops you. So being able to do this is the key point, being able to study maximal functions and improve, you know, Littlewood's theorem and whatnot on such spaces. And the other application that's just sort of fairly interesting is that the volume of the ball of radius r around x is just uniformly bounded from above by the volume and the corresponding of the ball of radius r in the corresponding space form. So, you know, if this is Euclidean space, it's a non-negative Ricci. This is just saying omega n r to the n, right? It's time for this one to go. So these are both one line. Let's go ahead and prove them. So remember, the rate of change of the volume ratio is less than or equal to 0. Right? So what does that mean? That means if we look at the volume, so let's prove 1 first. So look at the volume and the ball of radius 2r of x. Well, if we try to say that directly, we may be in trouble. But just divide it by the corresponding volume in our, I mean, as always, let's just say Ricci is non-negative, so I can write out explicit formulas for you, but it doesn't make the slightest bit of difference. Then if I were to divide this by the volume of the ball of radius 2r in Euclidean space, then we know this has an upper bound. Namely, it's bounded from above by v sub r, which is to say the volume of the ball of radius r, around x, over omega in r to the n. Okay, but I mean, gone. Our only fear here is that this would somehow have an r factor that survives, but we have an r to the n and r to the n. So for non-negative Ricci, it's actually 2 to the n. We know exactly what the constant is. So this says that the volume of the ball of radius 2r in our space is bounded from above by 2 to the n, and is the volume of the ball of radius r on the same point. No problem. And the proof of 2, well, I mean, again, let's just look at the ratio. So what is this statement here really saying? So if we take this and we divide it to the other side, all we're really saying is that v sub r is less than or equal to 1. That's the only statement we're making here, right? So why on earth would this be true? I mean, so we know it's monotone. Why should it be less than or equal to 1? Well, all we have to do actually is just, so for sure, it's less than or equal to v sub s for any s less than r. That's monotonicity. So in particular, it's less than or equal to the limit as s goes to 0 of this ratio. But I mean, so this is just going to the volume of the ball of radius r in Euclidean space. And by writing an exponential coordinate, you see this is just going to the volume of the ball of radius r in Euclidean space. So the ratio is just going to 1, which is the proof of the claim. So we have upper bounds on volumes of balls, and we have doubling conditions that say they don't grow too fast. Okay. So I have 5 minutes. So I'm going to entirely change topics at this stage. And that's enough for me to maybe say an important point, and that way we can start next time by me saying it again, and maybe it'll stick once it's said the second time. So this here is the geometry. It's the introduction, anyway, to what geometry of Ricci curvature is. There'll be actually vast sort of extensions of these results, but whatever. The other thing that Ricci curvature controls is analysis. You're able to say something about the analysis of your manifold. I mean, we already kind of hinted at that just when I was talking about doubling functions and maximum principles, but I mean this in a much more direct way. So we're going to be able to say that harmonic functions have gradient bounds, for instance. So if I'm on a random Riemannian manifold, well, I mean, it's smooth, which means, any harmonic function that solves an elliptic differential equation, it has some bound on the gradient, say, just because it's smooth. But that bound can degenerate. You may have no idea what that bound is, right? It could be a billion, it could be a trillion, whatever. The point is, if you have a lower bound on the Ricci curvature, then that bound is controlled by that lower bound on the Ricci curvature, right? So there's a direct way of saying that if you had a sequence, say, of spaces with lower Ricci curvature, that upper bound can't degenerate. It lets you say harmonic functions are well behaved, is really what it's saying. So this sort of began way back when. I mean, people were recognizing this stuff for a long time. And you can find a tremendous number of useful estimates in, say, the Shane Yao Red Book on this stuff. I mean, it's a big, thick book full of estimates on spaces with Ricci curvature. I mean, mainly on heat kernels and harmonic functions and so forth and so on. But sometime in the mid-'80s, some guys, Bakri and Emery, I mean, wrote down sort of some new estimates. And these new estimates, I mean, they were somehow, I mean, they just kind of proved the old estimates, but they did it in a much slicker way. I mean, first off, it's an easier proof. And second of all, I mean, I'll discuss this more as we go on, but it's somehow become a cornerstone of an entire different theory. I mean, it gives you ways of actually defining Ricci curvature on metric measure spaces, no smooth spaces floating around. So, I mean, this is, it becomes quite deep in and of its own right. But for the starters, we just want to write down what these estimates are and understand them. And maybe all I'll do for today is try to give some hint as to why one would expect lower bounds on the Ricci curvature to say something about the analysis on the manifold. I mean, if you were to try to tell somebody this in 20 words, what would you tell them? And the key observation here is what's called the Bochner formula. So you compute something. So that is, take some nice smooth function on any manifold. This is a nice smooth manifold, whatever. So U from M to R is a nice smooth whatever. And let's not compute the Laplacian of the function. I mean, we don't know what this is. Let's actually compute the Laplacian of the gradient of the function. So that is, let's just compute the Laplacian of the norm of the gradient of u squared. So then if you do this computation and just try to write it, I mean, do it on Euclidean space if you want first. Right? Then if you try to write out what this is, so this is sort of a claim at the moment, and we'll probably do it carefully. I mean, we'll definitely do it carefully next time. I'm not sure if I have time to do it, but it's an easy computation. It's a good exercise. Then what you end up getting is the following. It's, well, the first term is 2 times the gradient of u, inner product, the gradient of the Laplacian of u. Second term is plus 2 times the Hessian of u squared. And the third term is plus 2. All these 2's are coming from this 2, times the Ricci curvature applied to the gradient of u, gradient of u. Now, in principle, I mean, why is this interesting? So, I mean, this term here and this term here, if you do this computation on Euclidean space, you get just these 2 terms here. Right? This here is exactly what you get on Euclidean space. And now what's being told to you is that the correction term on a general manifold, when you make this computation, is precisely Ricci curvature. So Ricci curvature is exactly the error term of this formula holding on a general manifold. And if you wanted to sort of see why that's interesting or useful, the best way to do this is the following. So let's just assume 2 things. So by the way, most of the computations I'll be doing at this point forward will be of a more analysis nature. I think they're slightly less painful to actually follow the first time through. So imagine, so now I mean, this is for any function now, but let's apply it to a special function. Let's say Ricci curvature is non-negative, and this is not necessary. I mean, it's just, as always, it gets emphasized. It's a little cleaner when it's non-negative, so let's let it be non-negative. And let's say we're looking at a harmonic function, for the sake of argument. Then when we plug this in, well, the first term goes away. It's harmonic. And the last term at least has a sign, right? So this becomes bigger than or equal to 2 times the Hessian of u squared, which if you want, you could just call non-negative 2. But this implies that the gradient of u squared is subharmonic. This is a serious statement. We're saying that on a space with non-negative Ricci curvature, if we take a harmonic function, then its gradient is subharmonic. And if we have some feel for analysis, I mean, what can we do with subharmonic functions? Well, we can do maximum principles, right? So what this hints at, I mean, this is by no means a proof, mind you, but what this hints at right away is that, and you can make it rigorous, is that if, say, u is nice and bounded or something like that, if u is a bounded harmonic, this implies the gradient of u is bounded. And you can make this careful and rigorous, and it's true. So I mean, roughly speaking, this is how you get from harmonic plus non-negative Ricci equals bounds on gradients of harmonic functions. And what we'll get into next time is really a vast extension of this point by Bakary and Emery. It'll give us a much more precise sort of way of not only seeing that it's bounded, but seeing what it's bounded by and in terms of what. I mean, they're very nice, clean formulas for this. But I'm done for today.